Well, good afternoon or morning or evening, everyone. I'm Professor Rios, and welcome to week 2 of the summer course. Like last week, a lot of material is covered, so I recommend you watch this in installments. You can watch first part, the second part, and the third part. If you don't mind consecutively, great. Otherwise, time yourself and give yourself the best possible learning opportunity. I know it's a lot of material. I know the summer course is goes fast, and there's a lot of stuff that comes at you. So manage your time well. So we'll get started with week one. I'm sorry, part one of week two. Correction. So let's put that in presentation mode. And this week is all about wind. It's all about air pressure, circulation patterns of the atmosphere, and the ocean. These are the lesson objectives. Again, each lesson packet has a set of objectives um, stated right at the beginning. So, from listing the three ingredients of surface winds to describing the three phases of El Nino. Again, not everything is covered in the presentation. So, when you go over the material on the book or e text, or watching the video or looking at the slides on your own, realize that there is a totality of events that basically marks each week. I couldn't possibly cover everything in the video, otherwise, it would take entirely too long. So, just wanted to get that out of the way. So, pressure is basically the force of air directly above you, if you think of it as a column. So, pressure, like density, decreases very rapidly with height. So, for example, once you're at the top of Mount Everest, most of the atmosphere is already below you, 70% of it, in fact. And again, just as mentioned earlier, that the idea of pressure decreasing quite rapidly as you climb in altitude. The atmosphere is very dense at the bottom and very, 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 very thin at the top. And even that entirety of the atmosphere itself is quite thin in comparison to the entirety of the volume of the Earth, this big giant sphere that we live in. Again, air density, higher pressure, lower density, lower pressure. So both density and pressure decrease in the same fashion as you go up. Okay, so there it is. The nature of wind, think of wind as a recipe of three distinct features. One of them is the pressure gradient force. The second is the term Coriolis. And the third one, friction. Friction, I think you get. Pressure gradient force and Coriolis might be two that are less familiar to you. So let's begin with pressure gradient force, which is nothing more than the change in pressure as you move in the horizontal. Okay, so basically, usually there's an atmospheric temperature difference induced because of unequal heating. This has a lot to do with the fact that the Earth is made up of different surfaces: water, land, bright surfaces, dark surfaces, and that leads to a very unequal heating of the atmosphere. Winds tend to move from high pressure to low pressure, and winds are named for the direction from which they blow. So, for example, if the pressure gradient force were the only force acting on wind, air would simply go from high to low. Clearly, that's not the case. Now, here's a surface pressure map, some generic pressure. Think of this as a contour of pressure, and each line that you see here is called an isobar, which is nothing more than line connecting points of equal pressure. And so here at the center, you have a very low pressure, and as you go away from it, you have higher pressure. So notice where the lines are packed together, you have a tight pressure gradient, meaning the pressure changes very quickly as you move with the horizontal, so the winds are strong. In an area like in this map over Texas, where there are very few, if any, of those lines, the pressure gradient is weak, and therefore the winds are weak as well. Okay. Coriolis. Coriolis effect is a force that is imparted on moving masses of air and water as a function of the fact that we have a sphere that is rotating about an axis. And so the deflection is to the right in the northern hemisphere, and the deflection is to the left in the southern hemisphere. And this right here is what gives weather systems their very distinctive spin that you see on a weather satellite map. There is a very good set of videos on the class uh, playlist for this particular week, this particular section. They're usually pretty short, between 3 and 5 minutes. Highly recommend that you watch them on your own. You can watch and rewatch as many times as possible, and they explain this process particularly well. Now, the final ingredient, and by the way, this is the idea of Coriolis explained to you from the perspective of a merry-go-round with a kid at the center and somebody on the edge, which is like what would happen if you were looking down on the North Pole, which would be here, and this would be the equator. Okay. So there's the animation. Again, it's in the GEO101 SUNY YouTube page. Now, if pressure gradient and Coriolis were the only forces acting on winds, the wind would blow basically parallel to the pressure lines. That's not really what happens for the most part near the surface, because near the surface you have a friction layer, meaning buildings and mountains and the ocean and terrain and all that. And as a result, the wind near the ground tends to be more chaotic. As you go further and further up in elevation, the winds might be a little bit less so. So in the upper level, there's hardly any friction, so the winds blow pretty parallel to the pressure gradient lines or the pressure lines. Near the surface, let's go back to that image, you have the effect of friction, and as a result, the wind blows across the pressure lines, and that is in reality the kind of wind that we all experience near the ground. So here's the bottom line on winds: pressure gradient, Coriolis, and friction. This recipe will yield basically winds that blow across isobars or lines of equal pressure. Winds are converging towards low pressure and diverging away from high pressure. Specifically, here's an image from your text showing you that in a low pressure system, think of bad weather, the winds are blowing in towards the middle. See how the lines, if you connected all these arrows, they would all converge here. And during high pressure, the winds spiral out. Looked at it, and this is looking down. Looked at it from the side, low pressure implies bad weather, clouds. It's called a cyclone. And good weather or high pressure implies air that is sinking and spreading away. And this has the effect of drying and the effect of clearing, whereas this has the opposite effect. So a cyclone or low pressure is wet, cloudy, and an anticyclone or high pressure tends to be clear and sunny, for the most part. All right, let's look at some localized winds. So the first one and the most obvious one that you're probably familiar with are what are called sea breeze and land breeze convection loops. And these are convection loops. If you think back to last week and the idea of convection, convection is what happens when you heat a fluid. So near the during summer, mostly in springtime, the land will heat up quickly, and more so than the water. So you set up a low pressure here, high pressure in the ocean, and you get this loop going. And that's what's called a sea breeze, the wind blowing from the sea. On the other hand, you have a land breeze, and a land breeze is what happens during nighttime when everything reverses. And you get the land cooling very quickly and the water cooling less quickly. And as a result, everything sort of flips. And now the winds are blowing from the land towards the ocean. And here they're actually showing you with a little smoke pile what happens to the smoke. It blows inland, and at night that same smoke would blow out to the ocean. The other type of local wind is called a valley or mountain wind. And it's basically the same effect. It reverses from day to night. During summer in a valley, you heat the center, that air goes up, it cools, it sinks, and you create these convection loops. If you're a hang glider, this is kind of a big deal because you have to be aware of where the winds are, or you might actually be basically smacked up against the terrain. At night, the opposite happens. You have the winds basically blowing down the hill, converging near the middle of the valley, and then going up. And notice nighttime, daytime. And it's all a function of differential heating, how different areas and regions get heated differently, leading to this sort of fluid convection that's taking place. Okay. Now here's a map. This is sort of a generic weather map. Um, Um, Here you have high pressure over Canada, low pressure over Illinois. Notice how the winds, I sort of try to connect all the arrows with the blue and also with the red, and notice how the wind goes out of a high and into a low. And that is typical of what you find with a generic weather map over, in this case, the United States. Generic. This could be really anywhere on in the planet. I just picked the place that you would find a little bit more familiar. All right, the global atmospheric circulation. So it's called the GAC, global atmospheric circulation. This is a model. And if you remember back to last week, there was a question in the homework related to models. And why do we use models and why are they significant and important? And part of it is they tend to simplify things. And so in this particular model, you have the Earth broken up into regions 0 degrees, 30 north, 30 south, 60 north, 90 north. And generally associated with each, you have low pressure near the middle, where the sun heats the surface more vigorously. You tend to have high pressure near 30 degrees north or south, low pressure near 60 degrees north or south, and high pressure at the poles. And so, in the end, the atmosphere isn't this simple, but this simple model helps you to understand the basic patterns that you are likely to find. Okay, so the two areas that we're going to focus quite a bit on during this block would be the equator. So it's low pressure, the sun heats the ground, the air rises, that air cools and sinks, and you get subtropical high pressure at around 30 degrees north or south. And you get the same thing in the southern hemisphere. So this is a very simplistic way of looking at the atmosphere, but it yields a lot of information that gives you the basic setup that you tend to find on a day-to-day basis. And there is an animation found in that same YouTube page, playlist rather, for you to take advantage of. So here's an image of the atmosphere. Notice this is equatorial low. There it is, near the equator, not exactly over it. The characteristics of the equatorial low, or ITZZ, are intense heating, lifting air, low pressure, clouds, and rainfall. The opposite of that would be the subtropical high pressure, which would be found here or here. Notice on either side of that. And that's where you tend to find dry conditions, sinking air, generally clear skies. And that is generally where you tend to find deserts throughout the world, like the Sahara or the Arabian Desert. Okay? So the wind patterns that you associated with these pressure systems would be the trades, the prevailing westerlies, and the polar easterlies. And we're actually going to talk about this week simply because we're doing more than 1 week at a time compared to what the normal spring and fall setup would be. So these are the winds that you tend to find um, in association with those pressure patterns. Trade winds, westerlies, we live here, and then the polar easterlies. So looked at it from a perspective of January and July generic conditions. Notice how you tend to have in January high pressure, low pressure, high pressure, low pressure. Do you see the pattern? And then in the summer, you still have high pressure, high pressure, low pressure here, and the high pressures tend to move over Bermuda and the Pacific Ocean with low pressure to the north. So there is a symmetry that I hope you kind of see. In reality, the world isn't that perfect and that idealized, but this gives you at least a good sense of where things should be. So, from the perspective of planning, and you live in an area there where there's always high pressure, where what are you going to find there? Deserts, generally speaking. Okay. And why do you find tropical rainforests near the equator? Because it's usually low pressure throughout. Therefore, you're going to find lots of rainfall all the time. And here's an example. And again, it's hard to pick out perfectly where everything is, but you can kind of see how near the equator, think of it as a belt in the middle of the earth, you have this band of clouds, that's the ITZZ. On either side of that, you have an area of relative clearing, high pressure, then low pressure to the north, low pressure to the south of that, and then high pressure at the end. So it's a very symmetric. Notice low, high, low, high. So it's symmetric about the equator. And again, there's a real example animation of that found in the playlist for this week's material. And you find that playlist link on Blackboard as well. Regional scale winds. So monsoon will be the first one, and monsoon is a seasonal reversal of wind. That's a key term right there, or a key point. And you find them most notably in India. That's the one everybody kind of hears about. But they're found in the US, Southwest Arizona, New Mexico, Colorado, Utah. You find them in Africa, you find them in Southwest Asia, you find them in Eastern Asia as well. The most obvious one, the one that everybody seems to know about, would be the monsoon in India, which usually begins in the month of June. And here's the example of that. Notice in summer versus winter, notice how the winds literally reverse. Here's the example over Eastern Asia and Southeast Asia. Notice how the winds in summer are from the hotter, warmer, moister area, versus during winter, they're coming straight out of Siberia. Here's an example in Australia and an example over Africa. All right. Air sea interactions, how the atmosphere and the ocean influence each other. And that's key right there. There may be more ocean than land, but the atmosphere, it covers both ocean and land. So there is a significant transfer of heat. There's a transfer of precipitation and moisture. And so all that leads to weather. Okay. These are the ocean currents. Notice the ones in red versus the ones in blue. And if you live near a cold ocean current, you tend to live in a relatively drier climate than if you live near a warm current. Here's an example of the Gulf Stream coming out of the Gulf and finding its way north and east towards Europe. Here's an example of what's called the thermohaline circulation. And again, that is thermo, heat, haline, salt. So it's a combination of, it's a three-dimensional circulation that distributes heat across the Earth. And it does so in a three-dimensional sense. And so here, the dark blue belt is under the surface, and the white belt with a red arrow implies areas where it is a surface current. Okay? And this is significant because this is like the big radiator across the earth that redistributes heat, which drives weather. El Nino, or ENSO, is acronym for El Nino Southern Oscillation. And it's a recurring disruption in the ocean and atmosphere, especially in the Pacific Ocean. And the repercussions tend to be global. So El Nino is that. The Southern Oscillation is this. And you might wonder why those two places, and that's because they tend to have the same general pressure all year round. So when that pressure changes from that norm, something's happening. So it's like a little warning bell. And here is El Nino Southern Oscillation. This is what happens during El Nino. The winds tend to weaken or even reverse direction, and therefore the water flow tends to do the same. Here's the most significant and strongest El Nino of the last half century in 1997-98. And basically the idea of anything in the red is El Nino, anything in the blue is La Nina. So that's the first part. So if you want to take a break, by all means, do that. I'm going to get rid of this one here, and we'll begin with week 2, part 2. Again, if you want to take a little break, do so. Stop and come back or keep going. I'm going to take a sip of water and we'll continue. All right, moisture and water balance. So, these are the objectives for the lesson. Some of the key terms. This is probably, we went over this last week. So, what's the significance of moisture? Well, there it is. Your cell phone may not work as well, your visibility or your travel, safety, planning, air travel, of course, being the big one, right? So most of the water in the ocean is salt water. Most of the fresh water is locked up in ice in sheets and glaciers. And most of the liquid fresh water that we like is inside in the ground. So even though there's a lot of water out there, most of it is really not very useful to us. So again, of all the fresh water in the world constitutes about 3% of the total water. Of that, most of it is in ice sheets. So it's a very valuable resource for clear and obvious reasons. You'll know about the fate of moisture, evaporation, precipitation, condensation, and then that term that we discussed last week, evapotranspiration. The idea of warm versus cold air and the ability to contain or hold moisture. So if you think about a warm air parcel versus cold air, in cold air everything's more dense and packed together, so there is less space for H2Os. So usually when you think of moisture in the morning, like dew, do you ever think of dew at 3 o'clock in the afternoon? Ever? Think about it. You've never seen dew at 3 o'clock in the afternoon. It just doesn't happen. It's always a morning event. So in the morning, conditions are cooler, and therefore that condensation can actually begin to take place. So remember this definition, the idea of latent heat, the changes of state that involve either the absorption or the release of latent heat. Remember, latent heat, think of it as potential heat. Okay? Talked about evaporation. You'll know what evaporation actually is, but evaporation tends to be a cooling process. Again, take a hot shower in winter and come out of a shower and you feel immediately cold. Why do you feel immediately cold? Because it energy is required to evaporate that water from your skin, and as a result that removal of heat causes you to feel cooler. So that's evaporation. Now evapotranspiration is the combined evaporation from water and land sources. So think of grass and dirt and trees and so on. Condensation is the other way around. So condensation actually warms. And think about the best example I can think of. It's a hot day, and you are coming in from the outside, and you have a nice cold can of soda or juice or something that you want to drink. It's cold almost to the point of freezing, but not quite. Like it's like 33-degree liquid. You can't wait to drink it. You take it out of the refrigerator and you put it on your desk. And your room is not hot, but it isn't cold either. It's a warm room that you're in. And something happens. Somebody calls you on the phone. Something comes up, and you basically leave your can on the desk. And you come back an hour later, and you find a big puddle of water around your can. Where did that water come from? It didn't seep out of the metal that makes the aluminum can, right? It is the warm air in the room that literally touched the can, cooling it and condensing that air into liquid. You condense the moisture from the air into a liquid form. When that happened, heat was released in the form of latent heat of condensation, and the liquid inside got warmer. Then you open your can and you go, ugh, this isn't cold anymore. That's because latent heat of condensation helped to warm your liquid up. Condensation nuclei, this exists. In fact, every time you breathe, you take in a few of them. These are the measures of humidity. The three that you're most, well, there's two that you're familiar with, one that you're less familiar with. So specific humidity, there you go. Relative humidity is relative to something, and that something is temperature. So it's the ratio. So relative humidity is very fudgy because it changes throughout the day. The one that doesn't really change that much is dew point, and that is the temperature at which saturation occurs. So as let's go back to this. Let's go back to that. So relative humidity is the ratio of the amount of water vapor present to the maximum capacity for that specific temperature. So the lower the temperature, the lower the capacity of the air to hold moisture. Okay. Dew point temperature, on the other hand, simply tells you the temperature that you have to lower the temperature to in order to get dew. Get it? Dew point. Or in winter, frost. Okay. There you go. As the temperature increases, the water vapor capacity of air increases as well. Remember back to that image with the little nitrogens and the oxygens being further apart versus being close together. And here's the idea. This is not from your book. It's frankly a very old graphic, but it still gets the point across, I think. Same, the blue represents the amount of moisture in the air. Notice how it doesn't change. But what does change is what? The temperature. At 4 in the morning is 5 degrees Celsius or 41 Fahrenheit. At 10 a.m. is 16 or 61. At 3 p.m. is 32 or 90. So this warm air can hold 5 times more moisture than the air at 10 o'clock, which can hold twice as much as the air at 4 in the morning. When are you likely to experience dew? That would be here with a relative humidity of 100%. There we go. Clouds. Talk about the idea of condensation nuclei. These are the types of clouds. Not spending a lot of time on this. Just need to know that there are high, middle, low, and clouds of vertical development. And each of these tend to be associated with a type of front. We'll go over that in the next lesson. And as far as atmospheric moisture, besides rain and snow, you tend to have sleets, freezing rain, hail, which is associated with thunderstorms, and graupel, which are like little soft little balls that fall during winter. The idea of water balance, the idea of PE, potential evapotranspiration. So when the amount of potential evapotranspiration is greater than the actual precipitation itself, you have a desert or you lose water. When the precipitation is greater than the PE, then you have water gain, the tropics. So this is important because it's significant to agriculture. And here's the example of surplus versus deficit, depending on where you happen to be, a place like Baghdad, Tokyo, or Portugal. In Tokyo, there's always a surplus. In Baghdad, there's usually a deficit. In a place like Faro, Portugal, which happens to be a seasonal climate, you tend to have a mix of both. Air masses. what an air mass is. Don't define air mass by saying that it is a mass of air, because that doesn't tell you anything. Um, this is what an air mass actually is. And you tend to have these six categories. And you classify them as wet, very wet and dry, hot, warm, cold, and extremely cold. The ways of lifting air: convection. Remember, convection, the process, the physical process, is also referred to as convection in the atmosphere. So there's convection. You heat the air up, it bubbles, it turns into a cloud, and eventually that rains or snows depending on the time of year. And here's convection. Can you see it? Nice and obvious. It looks like little popcorn kernels. There is frontal lifting, and again, this depends. The fronts are different masses of air: cold, warm. A warm front is warm air pushing cold air out of the way. It has a very shallow slope, and it has a difficult time pushing air out of the way because cold air is heavy. A cold front, on the other hand, is cold air, which is heavy, pushing light, warm air out of the way. So the weather with a cold front tends to be more violent. Think about springtime versus warm fronts, which is what you can often find in fall and winter, which tends to be more sort of light and sort of gray skies as opposed to the vigorous cumulonimbus, big thunderheads that you see in winter and summer. So this is the idea of frontal lifting, comparing that to just basic convection here, which is just the hot, warm air bubbling up into what you see there before you. Orographic, this is what we addressed last week. The idea of wind over a mountain causing rain on one side, the windward side, and lack of rain on the other side or the leeward side. And here's the example from your textbook. The Cascade Mountains in Oregon and Washington. On the west side, you have green, lots of rainfall. On this side, you have very, very little rainfall. And that is, remember, an adiabatic process, which simply tells you as you go up in elevation, your pressure goes down and your temperature goes down. And remember the idea of lifting air. You force it to go up. You reach an area where your clouds begin to form. The air continues to expand and cool, but at a lesser rate. And that's because you've released latent heat to the environment. And it decreases at a lesser rate. And then it goes over the other side where you basically warm by compression, and it warms up pretty fast. And that's the idea of the dry adiabatic lapse rate. Thunderstorms, convective ones, here they are. Some general specific things about thunderstorms if you want to sort of stop it and take a look at this. And notice where you tend to find convective thunderstorms most intensely. Of course, the Amazon, the Congo, the Indonesian deserts. I'm sorry, rainforest rather. Look at the southeast US, Florida, the Caribbean. Tornadoes, here you're talking about the idea of obviously a violent storm, extreme low pressure, and it's a function of contrasting air masses, warm versus cold. air mass. It's very warm, very moist, very unstable. Lots of latent heat of condensation, which provides the fuel. This is different when we get into hurricanes. The fuel and the conditions necessary for that storm or that type of storm is very different. And notice where you tend to find the majority of tornadoes. Yes, we know we number one. And that's because in the United States, you have the perfect moist source in the Gulf, cold air source in the north, and the flat terrain in the middle. The perfect, perfect location for that to take place. Again, if you want to take a little break, there's one more presentation left, not as long, but if you want to take a break and come back to a little bit later, I recommend you do that. Or you can just watch straight through. All right, weather systems. So now here we're talking about actual like cyclones, whether they be mid-latitude cyclones or tropical ones. So again, the objectives for the particular lesson, the significance. The military is often involved in humanitarian disaster relief. Here's just some examples of some famous ones. Some of them from many years ago, some from as recently as Michael in 2018. So, tropical cyclones and hurricanes. A hurricane is a tropical cyclone. A tropical cyclone doesn't have to be a hurricane. And we'll get into why that is. So, a hurricane basically is something that is found within 5 to 15 degrees of the equator, north or south. They require warm ocean water. And these are the things that are usually associated. These are characteristics of a hurricane. Again, a hurricane is a name given in the Atlantic Ocean and the East Pacific Ocean. In the Indian Ocean, they call them cyclones. In the Pacific, Western Pacific, they call them typhoons. Same thing. This is a photo from inside Katrina. Yes, people fly into these things. And these are the 4 ingredients that are required. You need warm water. You need to be far away from the equator, or far enough away from it anyway. You have to have a pre existing disturbance. Think of it as a little embryo, a cluster of storms, an area of low pressure that's already there. And you have to have no significant wind shear with height. Wind shear is what happens when wind changes direction with height. Okay? So it can't change too much direction or it can't change too much speed. And here's, for example, this would be a little disturbance that's available. This is how they grow and how they dissipate. Obviously, they don't last forever. Usually the winds and the pressure near the eye changes significantly. You've heard the eye of the storm, the calm inside the eye. It's a real thing. It means you had strong winds before and you will have strong winds after. Here's where they tend to form generally. Notice none near the equator and none near South America or most of Africa. And that's because the waters either are too cold or there's not enough warm water. This one stray one formed in 2004. It's the only recorded one in this part of the world. These are the movement patterns of hurricanes. When they first form near the equator, they tend to move east to west along the trade winds. And then they turn to make a turn to the north and to the northeast, right around subtropical high pressure and into the westerlies. And that's when they affect our region. So here's an example from 1999. Notice how a lot of these storms travel east-west, and then at some point they begin to go a little bit further north, and then boom, they make the turn. Some of them make it, it takes a while. Some of them will never make it. So it really depends on a particular, uh, particular event. But generally speaking, they all follow this pattern: east-west near the equator or in the tropics, and make a turn to the north, and then northeast, and then they move into the zone of the westerlies. Okay. Here's an example. This is the SAFFIR-Simpson scale, which is basically uh, a function of wind and damage. So category 1, minimal damage, to a category 5, which would be catastrophic damage, and everything in between. So you have category, pressure, and wind, and the related damage that tends to be associated with it. Uh, Usually, the biggest deal with a hurricane is most likely flooding and storm surge near the shore. Of course, winds are significant, clearly. So here's the idea of storm surge. Oh, sorry. Um, this may be mean sea level. So what happens is you have low pressure, so the water can rise, and then the winds push that water in. So storm surge is a combination of lower pressure and wind pushing that water inland. And wind tends to do the majority of that pushing of water. Here's the idea of flood damage. This happens to be a human issue. Some of the levees in Louisiana near New Orleans that collapsed. If you ever doubt the power of wind, here you go. Like if you ever doubt the power of wind, look at that. Or look at the power of water moving this entire casino from here. Crazy, isn't it? Here's what wind did. This is near Homestead, Florida, associated with Hurricane Andrew in 1992. Here's where hurricanes tend to be most damaging. And the time of the year, September 9. That's the peak of hurricane season. Why? Because it takes all of May, June, July, and August for the water to heat up to the point where it can then release it in the form of wind and rain. Hurricanes have an environmental consequence besides the obvious. They tend to cost money. They tend to put coastal populations at risk. They affect insurance, oil and gas, economic nodes like U.S. ports. So there's a lot of sort of related damage associated with one. Katrina, for example, still the costliest disaster of all time, in terms of natural disaster. Think about it, almost half a trillion, a quarter trillion dollars. And again, here's New Orleans, water to the north, water to the east, water to the south. And there it was in 2005. Here's the idea of a mid-latitude cyclone. So in a mid-latitude cyclone, unlike a hurricane, you have competing air masses. So you tend to have warm air, cool air, cold air, depending on where you are. And this is what happens before, during, and after a front. and the kind of conditions that you expect. And this dash green line, so it goes from the cold air to the warm air to the cool air, is what you see here. So this line is this line that you see there. So, and that's the block. That is the lesson for this week. Next week, week 3, we get into the climate block, and so a completely different type of material. Um, I hope you found it reviews. Again, I know it's a lot of stuff that you have to watch. So my recommendation is simply watch it in a piecemeal form if that works better for you. Otherwise, I hope you're doing well, and we'll talk to you soon. Bye.